Assalamu alaikum everybody. Welcome to the second part of our lecture on searching techniques in AI. This part is going to be on informed search, otherwise known as heuristic search. And these are the list of topics. First, we will take a little motivation why we want to learn about informed search, given that we have seen many searching techniques which are uninformed. What makes informed search better than uninformed search? So first we will learn about heuristic functions, because actually this informed search, they depend on a function called heuristic function. So what are heuristic functions? Once we learn that, then we will look at the two main informed search strategies, namely the greedy best first search, GBFS, and the A-star search. Finally, we will try to look at the conditions for optimality of heuristic search, and this will lead us to evaluate the performance of A-star search particularly, because this is the best among the two. And in the last part, we'll take a small summary comparing between A-star and uniform cost search that you already know, so that you can see clearly what is the difference between A-star and UCS, which is an uninformed search. Motivation for informed search. All the informed search strategies that we have discussed so far, they have one common characteristic. They select the next state to be explored based on some cost function, call it F, that depends only on the start state. Shown in this diagram, normally we will expand starting from this start state, keep putting the successors in the frontier, and then we look at the frontier and decide which one of them is best to explore, and so on. So this decision on which node to explore is purely based on the function f, which does not depend on the goal state. It's only depending on the start state. Okay, this is what I'm saying here in this second point, that the uninformed search, they have no idea of the cost from the current state to the goal state. Okay, they can only tell you the information from the start to the current state, but they have no idea how much it will take to reach the goal state. For example, if you take the UCS, uniform cost search, that F is actually what we call G, the function G. The function G here being the total cost of the current shortest path from the start to the current node A. So if you look at the diagram here, G is only telling you from the start to A, this is the cost. It costs 10. From the start to B, it costs 5. From the start to C, it costs 15. And therefore, UCS will say, okay, since this is the least cost so far, we should explore it. It is likely to be on the cheapest path to the goal. But without knowing any idea what happens from this point to the goal, we don't know. So the problem is there is no guidance as to how far any given state is to the goal. And therefore, a good solution might be to design another function, call it H, that will give an estimate of the distance between a particular state to the goal state, shown in this diagram. Wouldn't it be nice if we know from the current state how much it will cost to the goal state? An estimate, not necessarily the actual cost. If we know the actual cost, then there is nothing to do. We can just conclude we have found the the shortest path. But wouldn't it be nice if we can have a function that can give us an estimate? So estimate doesn't necessarily mean it is going to always be correct. It may be wrong, it may be correct, but at least give us an idea how much it will cost from the current state to the goal state. It may have cost smaller value to reach B, but if B will cost much more from the present B, if it will cost much more from the B to the goal state compared to from A to the goal, definitely it will have been better to follow the A then instead of following B. So this is the point. Unfortunately, all the uninformed search, they have no idea how much it will cost, even an estimate from the current state to the goal state. All they know is the cost from the start state to the current state. So this is a problem. And this is why we need to learn informed search, or this is the motivation for wanting to learn about informed search. Let's look at now heuristic functions. Heuristic function HS represents an estimated cost of the cheapest path from a particular state S to the goal state. And heuristic functions, naturally, they are domain specific. Okay, so you need to have a lot of background about the particular problem for you to be able to come up with this heuristic function. In other words, they cannot be computed solely from the states and the transitions in the current problem. It will need some knowledge about the problem. Okay. If we can compute it from the problem itself, then it means we already know the optimal path. Okay, but it is not clear from the problem itself how to compute or how to define this heuristic function. It depends on knowledge about the domain of the problem. But we have some constraint for the heuristic function HS. If S is the goal state, then H of S should be 0. We are already there. Okay, so any heuristic function you define must assign 0 to the goal state. But for all other states, HS should be greater or equal to 0. So this is a very important condition. The second one is that if H of S1 is less than H of S2, then we guess it is cheaper to search the goal from S1 than from S2. Okay, so if heuristic function tell you the cost from S1 to the goal is some value which is less than the cost from S2 to the goal, then it should be cheaper, to follow S1 rather than go through S2. Let us give examples of heuristic functions so that you can have a better feeling of what they mean. Example 1, for the route finding problem from Arad in Romania to Bucharest, a natural heuristic function could be the straight line distance from a particular state to the goal state. Just straight line distance, irrespective of whether there is a road there or not, just the straight line distance. Okay, this is another word known as the Euclidean distance from point A to point B. Okay, let's look at updated map of Romania, where in addition to what we have seen before, now we have added the distances in red from each state to the goal state, which is Bucharest. So this is a straight line distance. If you are just to draw a straight line from Arad, for example, to Bucharest, ignoring any road. Just straight line distance from this point to this point is going to be 366 kilometers. Obviously, if you're already in Bucharest, the distance is 0. You're already there. The test here, because it's near to Bucharest, it costs only 100 kilometers. This is 80. Straight line distance between Iasi and Bucharest is 226. Okay, and so on and so forth. So this is just straight line distance. Just measure the distance, ignoring whether there is a road there or not. Okay, so this should give us an idea. For example, if you are here in Fagaras and you are trying to reach Bucharest, the fact that it will cost you only 176 from Fagaras to Bucharest, whereas it will cost 253 from Sibiu. It is better for you to start from Fagaras rather than from Sibiu and so on. So this is the idea. Straight line distance can be used as a heuristic function. Let's take another one. You remember the maze problem that I showed you, where we even have a program that is computing that. So for that, if you want to know an estimate for a certain state, in that case any particular cell in the maze, then a heuristic function could be what is called Manhattan distance from that state to the goal state. Manhattan distance simply means the number of steps you need going up or down, left or right, from the current state to the goal state. For example, if you are here, then to reach the goal state B, it is only 1 step. If you are here, it is 2 steps, 1, 2, and so on and so forth. So the numbers here in white are actually the Manhattan distances from each state to the goal state B. For example, this state, it will cost you a Manhattan distance of 16 to reach goal B. So notice that the Manhattan distance ignores the wall. Just like in the straight line distance, we ignore whether there is a road or not. Here, just count how many steps from the current state to the goal. So for example, if you are here, let's see how much it will cost you in terms of Manhattan distance to reach B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is the idea of Manhattan distance. How many steps will it take you to reach from the current state to the goal state? So obviously this can be a good hint if you are trying to explore which state to go next. For example, if you are here, you remember with the depth first, when we came here, instead of going to the right, it went to the left. Okay, so now with the knowledge of the Manhattan distance, it will tell you, no, this side is closer to the goal, so go to the right rather than go to the left, and so on and so forth. Of course, it should be clear that the Manhattan distance is not necessarily correct. It's just an estimate. For example, it tells you here that the distance from this cell to the goal is 2. But actually, it's much more than that because there's a wall. You cannot just cross. In fact, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It actually will cost you 12. Okay, so this is the idea. It's just an estimate, but at least it's better than nothing, as we shall see. So the first one is saying the total number of misplaced tiles. Just count in this particular state how many tiles are misplaced. This will give you heuristic value for that state. Another one is the sum of Manhattan distances of each tile from its position in the current state to its correct position in the goal state. Let us see what this means with an example. So suppose you have a particular state S. Notice that this is not start state, this is any state S. And this is the goal state. So the question is, can we have an estimate of the cost from this state S to the goal state? So H1 is telling you just count how many tiles are misplaced. Obviously 1 is not in the correct place, 5 is not, so we have 2. Similarly 3, so we have 3. 8 is not in the correct place, so 4. 2 also, so 5. And 4 also is not in the correct place, so we have 6 so far. But if you look, 6 is in the correct place, and 7 is in the correct place. Therefore H1 of S is going to be 6. Simply the total number of misplaced tiles in state S. Okay, the H2 is similar to what I showed you there with the maze example. Simply count for each tile what is the Manhattan distance from its position here in S and its correct position in the goal. So for example, the Manhattan distance for 1 is 1. You just move it one step to the right and it will reach the correct place. So for this particular state, actually, this is the value of H2. So for 1, it is 1 as we said, but for 2, it needs to move 2 places, either to the right, then up, or up, then right. Similarly for 3, we need to bring it here. So how many steps are needed? So you can say 1, 2, 3. Okay, but 4 is very near to its correct place, so just 1 step is needed. And 5 require 2 steps. So or to the right and then down. Okay, but 6, as we said, is in the correct place, so its Manhattan distance is 0. 7 is also correct, 0. But 8 require 3 steps. 1, 2, 3. Okay, so if you add all of this, you will get 12, and that is the value of the heuristic function H2 for this particular state. So this gives you an estimate, yani, from where you are now, how much do you need to reach the goal? And that should be able to help you to determine which state is the best to actually explore, rather than depending only on the start state. So with this information now, we can start to look at the informed search strategies. And the first of the 2 informed search strategies we shall look at is called greedy best first search. I'm sure you are familiar with greedy algorithms. They try to utilize the local information. They assume that what is good locally should also be good globally. All right, it's not always the case that it will work, but if it works, it normally gives a good solution. So here is the greedy best first search. It says expand the node that is closest to the goal on the ground that this is likely to lead to a solution quickly. In other words, it evaluates nodes by using just the heuristic function. So instead of looking at how much it needed to reach the current state, No, it will simply look at how much it needs from the current state to the goal. So the Fn becomes equal to Hn, just depending solely on the heuristic function. This is what the greedy best first will do. So for example, let us see how this greedy best first search will work with our route finding problem in Romania, using the straight line distance as the heuristic function. Okay, so I show part of the graph because we don't show everything. We are only interested from Arad to Bucharest, and you can see the relevant states and their estimated straight line distances. So from Arad, as we said, we need 366, Sibiu 253, Rimichu Vilsi is 193, and so on. And Bucharest is 0, of course, because we are already in Bucharest, so the cost of Bucharest should be 0. So looking at this, let us try and see how will this search strategy work if we start from the initial state Arad, trying to reach Bucharest. So we're going to explore the tree as usual and see how it goes. So I repeat the graph here, but we're going to start initially at Arad. Okay, so we are only depending purely on the heuristic distance. Alright, so since this is the only state, we have to explore it. In the second stage, we're gonna explore Arad. So from Arad, as we can see, the nearest state we can go to is Sibiu with 253 heuristic value, followed by Timisoara, which is 329 cost from Timisoara itself to the Bucharest. It costs 329, so we're gonna have that. And then the other town we can reach from Arad is Zerind. So Zerind, it will cost from Zerind to Bucharest 374 miles or kilometers, whichever unit you want to use. So this is the situation so far. After exploring Arad, these are the 3 states that are going to be in the frontier. So since this greedy best first search is looking at things greedily, it will rely only on this value and see which is the smallest. Obviously, Sibiu has the smallest value. Therefore, it is going to try and explore Sibiu next. Okay, so let's see what happens after exploring Sibiu. Now, Sibiu is neighboring Arad, so you can choose to go back to Arad. We will see that this time the problem of coming back to this state is going to be avoided because the cost is going to be much more than the others. So, but anyway, let's list them. So from Sibiu to Arad, you will say the cost from Arad to Bucharest is 366. So that's what you will put here. Okay, not the cost from Sibiu to Arad itself. No, how much it will cost from Arad to Bucharest is 366. Okay, what about Fagaras? Well, Fagaras, it costs only 176 to reach Bucharest from Fagaras. So you put that. Oreda is even further away from Bucharest, 380. And Rimichu Vilsi will cost much smaller value, which is 193. So this is the expansion of Sibiu. And now, with all these states in the frontier, remember these are still in the frontier, Timisoara, Zerind, and now this additional 4. The question is, which is the nearest to Bucharest? Because this greedy best first search is only interested in the smallest cost to the goal. The smallest cost to the goal. Well, the smallest cost to the goal seems to be 176. Okay, So it's gonna go to Fagaras next. Alright, therefore it will try to explore Fagaras. So let us see that in the next step. Yeah, so from Fagaras it could choose to come back to CBU, but that will cost 256 to Bucharest, or in fact it can reach Bucharest directly. Okay, so it will put that, and then now clearly the algorithm will stop because we have reached Bucharest. So far this is what GBFS has shown us. This is the route. The question is there a better solution, or is this the optimal? It turns out actually there is a better solution. Okay, if we had gone through Rimici-Vilsi, it will have cost 32 kilometers shorter, because following the other paths which the algorithm gave us actually will cost 450. If you add this 140 plus 99 plus 211, you're gonna get 450. But if you add 140 plus 80 plus 97 plus 101, you're gonna get only 418. So clearly 418 is smaller than 450. In fact, smaller by 32 kilometers. So the conclusion therefore is, unfortunately, this algorithm doesn't give us the optimal solution. It tries to give us the best it can, but because it is greedy, always looking at the one it can see locally as being the best, it will choose it. It will not necessarily give you the optimal solution. How about completeness? Is the algorithm complete? Again, unfortunately, GBFS is not necessarily complete. Let's take an example. So consider the problem of getting from ERC. So this is ERC to Fagaras. So we want to go from ERC to Fagaras here. Notice that these values are still the estimate from these cities to Bucharest. They have nothing to do with from ERC. So ignore the red values for now. Okay, but assuming we want to move from ERC to Fagaras, the question is, what will this algorithm say? Okay, well, obviously from ERC we're gonna expand, and we will see that there is NIMT and there is VOLC. But because if you take the straight line distance from NIMT to Fagaras and the straight line distance, okay, from Vaslui to Fagaras, you will see that this distance is longer. Okay, and therefore the algorithm will choose to expand NIMT first. Yeah, so that's what we are saying here, that the heuristic function will suggest that NIMT should be expanded first because it is closest to Fagaras. However, the solution actually is to go Vaslui, then Urziceni, and then Bucharest, and then Fagaras. This is the correct solution, because this, as you can see, is a dead end. You cannot reach anywhere from NIMT. Okay, but unfortunately our algorithm will choose to expand NIMT first, and it is a dead end. Basically it's going to take you back to ERC. So ERC will again go back to NIMT, and the algorithm will end up in an infinite loop, because it will never go to Vaslui. So it will not be able to find the correct solution. It will just be moving between these two states. So this is a problem. It means therefore that the algorithm is not complete. Okay, that's what we are saying here, that the algorithm will never find this correct solution, because expanding NIMT puts ERC back into the frontier. And because ERC is closer to Fagaras than Valsui, Iyasi is going to be expanded next. So it's going to be just moving between this, so it will end up in an infinite loop. This is a problem. So unfortunately, GBFS is neither complete nor does it guarantee optimal solution. This is especially with the tree version of the algorithm. Remember, for each of this algorithm, we can choose to use the general tree search or the general graph search. So for the tree version, definitely it is incomplete and it may not give you an optimal solution. However, here we are saying the graph search version is complete, particularly if the state space is finite. But even that one is incomplete, obviously, if the state is infinite. What about the complexity in terms of space and running time? Just like the uninformed search, actually the informed search still, their complexity is BTM. The only thing we are trying to see is if this M can be reduced. Okay, M is the maximum depth of the tree. The only thing the heuristic function are trying to do is to see if they can reduce the M, because the more we can reduce the M, the better result we will have. But theoretically, the running time is still exponential. Okay. Yes, so this is what I'm saying here, that with a good heuristic function, the complexity can be reduced substantially. Okay, so let us look at the second informed search. The first one didn't do very well. Let us see if this one can do better. So this is called A star search. We read it as I have just read it. A star search. So this is the most widely known form of best first search. It combines GN, which is the cost to reach the current node, and HN, that is the cost to get from the node to the goal. So it's going to utilize not only the heuristic function, which will tell us the estimate from the present state or the present node to the goal, but also what it knows from the start state to the current node. So the Fn is going to be Gn plus Hn, not just Hn as in the case of greedy best first search. No, it will utilize the knowledge it knows so far. It has costed this much to reach the current node, plus the estimate of what it will take to reach the goal. So this is the function it's going to use. So we're going to try this again with the route finding problem in Romania, step by step, to see how this A star search works. So we're going to use the same map. Again, remember the values in red are the estimates from each state to Bucharest. So let's start again from Arad. Now here, as you see, we will be adding the cost to reach where we are plus the cost from where we are to the goal state, which is Bucharest. So obviously in Arad, that is the starting state. So it didn't cost you anything to reach there. You're already in Arad. But you know the cost from Arad to Bucharest is an estimated value of 366. So anyway, since it is the only state, we have to expand it. And from it, we can reach the three states: Sibiu, Zerend, and Timisoara. Now here, what you will do is you will add the cost from Arad to Sibiu, which is 140, plus the cost it will take from Sibiu to Bucharest, which is an estimated value of 253. This is the straight line distance from Sibiu to Bucharest. So these two values, if you add, you're going to get 393. And similarly for Timisoara, it cost from Arad to Timisoara 118. So plus the cost from Timisoara to Bucharest, which is an estimated value of 329. The straight line distance, if you just do a straight line, this is what it will cost you. So that gives you 447. And similarly for Zerin, it will cost you 75 plus 374. So looking at these sums, clearly the sum of 393 is smaller, and therefore again we're going to go to CBU next, not Zerin and not Timisoara. We're going to go to CBU. So we're going to explore CBU next, and now this is what you will have. So from CBU, you can choose to go back to Arad, but this time you don't just say 140 because it costed you 140 to reach CBU. So now you have to add that 140 again. So you're going to get 280 plus the cost from Arad to Bucharest. So 280 plus 366 will be 649. So this cost alone will actually prohibit you from coming back to Arad, because it's going to be too much. All right. What about Fagaras, which is also nearby? So here again, you have to mind yourself how much it costs you to reach CBU, which was 140, plus the cost from CBU to Fagaras, 99. So if you add these two, you will get 239. So this will be the actual cost to reach from Arad through CBU to Fagaras. So once you reach Fagaras, now you have to add 176 as an estimate from Fagaras to the goal of reaching Bucharest. Okay, so that's what we have here. It will be 415. Okay, similarly for Oradia. Oradia is very far away. 140 plus 151 and then plus 380, so 671. And finally 220 for Remutubility. It will cost you a total of 413. Good. So now based on all these values, you look at the smallest. So the smallest one is the one you're going to explore next. So this is 413 seems to be the smallest. 413, which is Remutubility. All right. So this is contrary to what we saw last time. The algorithm for greedy best first search, it chose Fagaras and it went to Bucharest from Fagaras. But this algorithm is telling you no, don't go to Fagaras, because if we add the cost from Fagaras to the goal, you're going to get more compared to if you go to Remutubility. If we add the estimate to the goal, the total is still only 413. So this is the difference between this algorithm and the previous one. It's looking not only ahead but also backward. Okay, right. So actually it's gonna explore Remutubility next, and that's what we have here. So from Remutubility we can reach well, there is one state that is not being shown here. It is carryover. If you look at the bigger graph, you will see it. Okay, and then there is Pitesti. You can reach Pitesti, and of course you can go back to CBU, but that will cost you double the amount, 80 plus 80 back, and then plus cost to the Bucharest. So total is going to be 453. Now here you have to be careful. It looks like 417 for Pitesti seems to be the smallest, but actually it is not the smallest. It is actually Fagaras that is the smallest with 415. Remember, all these white cycles, they are in the frontier. All right. So the priority queue actually will push Fagaras to the front of the queue. All right. So actually, it is Fagaras that will be explored next, not Pitesti. So from Fagaras, we can go to CBU and we can go to Bucharest itself. So this is what you have in the next step. So we have CBU, which will cost 591, and Bucharest, which will cost 450. However, the fact that we have Bucharest in the queue doesn't stop the algorithm. Because if you look at the value of reaching Bucharest from Fagaras is 450. Whereas here we have Pitesti with 417, which is a much smaller value. So actually the algorithm will go ahead and explore Pitesti first to see maybe there is a better way to reach Bucharest from Pitesti than Bucharest. In other words, the algorithm doesn't accept a goal at the point of generating it, only at the point of exploring it. Okay, so this is the note I'm making here. It's a note that Bucharest appears on the frontier from Fagaras, but it will not be selected for expansion. Why? Because its function cost is 450, which is higher than the cost of Pitesti. In other words, what the algorithm says is there might be a solution to Pitesti whose cost could be as low as 417. Okay, so therefore it is not wise to settle for 450. So actually Pitesti will be explored next, and that is what we will see next. And truly, from Pitesti, as you can see, it costs only 100 to reach Bucharest. So the total cost is 418. All right, 418 to Bucharest from Pitesti. And if you compare that with the original cost of reaching Bucharest 450, this 418 is much better. And therefore, now when we are trying to explore, this is the smallest value among all the white cycles. This is the smallest, so Bucharest will be accepted, and because it is the goal, the algorithm will stop. And as you can see, in this case, it managed actually to find the optimal solution, because Arad is going to go to CBU to Mitrovica, from there to Pitesti, and from there to Bucharest. It's similar to what we saw earlier. All right, so this is the idea. Now the question is A star optimal? So the optimality of A star depends actually on the heuristic function Hn. For the tree search version, A star is optimal provided the heuristic function Hn is admissible. We will explain what it means for a function to be admissible in a moment. What about the graph search version? So the graph version of the algorithm, of the A star algorithm, will be optimal again if the heuristic function is consistent. So again, we're going to explain both of these two terms. What does it mean for a heuristic function to be admissible, and what does it mean for it to be consistent? So admissible heuristic. Define H star S to be the true minimal cost to the goal state from state S. So let us say this is the actual minimal value. Then a heuristic function h is said to be admissible if it is always less than or equal to that minimal value. Okay, in other words, a heuristic function is said to be admissible if it never overestimates. It always gives you a value that is either less or equal to the actual minimum, but it never gives you something more. So if a function is like that, it is said to be admissible. And clearly, the straight line distance is admissible. Okay, because as we know from the algorithm course, if you have two points, then the distance, direct distance from these 2 points is going to be shorter than going through a third point. So going through here and then here, okay, this is going to be the smallest always, and therefore the straight line distance heuristic function is definitely admissible. And you cannot reach these two. You cannot reach from this point to this point in any shorter way. Okay, so therefore the straight line distance gives you the smallest value always, the smallest estimate. Yeah. Okay, and that is the meaning of admissible heuristic. And we are stating here that if Hn is admissible, then A star using the tree search is actually optimal. Okay, yeah, so A star is optimal provided the tree version of A star is optimal provided the heuristic function is admissible. And since we know that the straight line distance is admissible, the example we just saw will actually give us optimal solution as we confirmed. Okay, the second term is consistent. When do we say a heuristic function is consistent? A heuristic function is consistent if for every node n, every successor n prime of n generated by any action A is such that h of n is less than or equal to the cost from n to n prime based on the action A plus the heuristic value from n prime. Okay, let's try and explain this by diagram. So basically what it is saying is, suppose we have two states, n and n prime, where n prime is a successor to n. Okay, then the heuristic function h will be consistent or monotonic or non-decreasing, if you like, if the estimate that, or to the goal that you're going to get from n is going to be less than or equal to the cost from n to n prime plus the estimate from n prime to the goal. Okay, as you can see. So this cost, the cost of the step cost, that is from n to n prime, is what we call CNA n prime. If you add that to the estimate given by the function h itself, from n prime to the goal, you will see that the estimate from n is always less or equal. Okay, so again, this is clearly the triangle inequality. So if your Hn behave this way, it is said to be consistent, or it is said to be monotonic. We're going to try and prove this quickly. So let us say H is consistent, and let's see if we can prove that it is actually monotonic. Now, by definition, Fn prime is the cost from the start state to n prime plus the estimate from n to the goal. This is by definition. Okay, according to our function, it is always the cost from the start to the current node n prime, so which we call g n prime, plus the estimate from n prime to g, and that will be given to us by the heuristic function h. All right, but g n prime, as we can see, will be the cost to n, which is gn, plus the step cost from n to n prime. In other words, this gn prime can be expressed as this plus this. Okay, good. So, but from the statement that h is consistent, we know that hn is less than or equal to the sum of these two values. These are the two terms we are having, the sum of this plus this. So this is greater or equal to hn. So if we replace this 2 by hn, we're going to get something greater. All right? And therefore, this what we have here will be greater or equal to gn plus hn. But gn plus hn is actually just fn. So what this means is, if we're going to reach n before we reach n prime, then our f at fn prime is going to be bigger than f at n. And therefore, it means f is actually increasing. I mean, it's not decreasing. Fn is non-decreasing. Yeah. Okay, so basically, this is what it means when we say if a function is consistent, clearly it means it is non-decreasing. Now we have a statement here that if hn is consistent, then A star using the graph search is actually optimal. Okay, to summarize now, let's look at the performance of A star. In terms of completeness, it is definitely complete. In terms of optimality, from what we have seen so far, there are two cases. If A star is implemented using tree version, then it will be optimal if hn is admissible. Simple admissibility is enough. However, if A star is implemented using graph search, then it will be optimal if hn is consistent. All right, that's what we can say about the optimality of A star. In terms of complexity, the time complexity is exponential in the worst case, although a good heuristic function will try to reduce to make it better. A perfect heuristic function will actually give us BD. Okay, although it's very difficult to get a perfect heuristic function. So usually we can say it's exponential. But memory space is exponential because we're going to store each generated node is going to be stored in memory. So the memory complexity is actually exponential, bit power d. Okay, so this is the performance of A star. Generally, it is much better than all the uninformed search that we have learned so far. To give you a better idea of what it does, let us compare it with UCS. So A star versus UCS, uniform cost search. So let us suppose we have states marked here by star. So this is the start state, and then we have two states A and B, and then we have goal state. As we know, UCS, basically it will be looking at the total cost to reach a particular state. Yani it has no bias. It is just going to look at the values and see which of them gives you the smallest value so far from the start state. Okay, so the order in which the uniform cost search will look at the states. For example, A and B have exactly the same distance, so they will be looked at before any longer path. In other words, there is no bias. If you start from here, basically you're just exploring. Yani there is nothing telling it, look, go to B first, because it is nearer to the goal. The uninformed search has no idea where the goal is. Therefore, it will just be looking at these two states as being equally likely, A and B. Okay, this is the idea. What about the A star search? A star search, however, has a hint. The heuristic function will tell it, look, this B is nearer to the goal than A. Therefore, you should be biased towards going to B. So you can see the cycle of A star is being elongated towards the goal. This is the idea. And the better the heuristic function, the more it will be elongated towards the goal actually. So that is why it will be able to reach the goal much faster compared to the other uninformed search. Uninformed search, they have no idea where the goal is. So they will just be looking at all the states equally likely just based on the information they have so far. But A star, because it is using the hint it got from the heuristic function, it will be moving closer to the goal, and eventually it will reach the goal much faster. This is basically what these diagrams are trying to tell us. And this is the end of this lecture. Thank you very much.